Hello everyone, I'm Jovan, and today I will present our work on HardHarvest, hardware-supported core harvesting for microservices. Microservices are emerging computing platform. With microservices, we break the large monolithic application into many small interdependent services. Each service implements a separate functionality, and services communicate with each other to create the end-to-end application. With this approach, we have many benefits. We have more scalable system, we have simpler design of applications, and also easier way to manage hardware at large data center scale. For these reasons, major companies such as Uber, Netflix, Amazon, they all have their infrastructures based on microservice systems. However, there is a big challenge with microservices. Namely, they have very low core utilization. This low core utilization stems from two primary reasons. First, to accommodate the peak load of microservices, users typically over-provision them. As you can see here in this plot, I showed the CPU utilization for 3 large Microsoft services over 1 working day. We can see that most of the time we have very low load with sudden load spikes. In order to have good performance, even when we have these load spikes, we need to provision more resources than needed on average. That means that on average, we will underutilize those resources. In addition, even when we have high load for our services, each of these requests are not fully utilize the resources. The reason is that these requests will be frequently blocked, either on I/O to go to the storage or to call other remote services. As a result, for these two reasons, we have very low utilizations of cores and heavily underutilized resources. In this plot here, I showed the CDF of average and maximum CPU utilization for Alibaba's microservices. We can see that 90% of services have maximum core utilization less than 40%. This is a huge waste of resources. A promising approach to improve the utilization in these environments is core harvesting. The idea is to collocate latency critical microservices with some other batch workloads. So in primary VMs, these are VMs that run latency critical workloads, and those are the VMs where user requests a specific number of cores. So here, we need to make sure that all the time users will have enough requests to run their workloads. On the other hand, we have harvest VMs that run batch workloads in the background, and for those, we have only guaranteed minimum resources, but they can dynamically span more requests and more cores as the cores from collocated primary VMs are becoming idle. So when one of the core in the primary VM becomes idle, Harvest VM can take this core, steal it, and then run some of the threads of its own to improve the utilization. Then, when the primary VM needs the core back, we need to return it from the Harvest VM back to the primary VM. In this way, we will improve the resource utilization because now we use more cores, and we can also improve the throughput of Harvest VMs. However, because now we need to go back from the Harvest VM to the primary VM whenever we have new requests coming in, we have increase in the tail latency due to the software overheads of this process. So why do we have high software overheads? There are two primary reasons. The first is the process of expensive core reassignment. Moving one core from one VM to another involves 2 hypervisor calls, first to detach the core from the first VM and the second to attach it to the second VM, and also we need to go to the expensive cross-VM context switch. So if we take Desktop Bench open source microservices, we have no harvesting case, we can see the tail latency at P99 will be around 4 milliseconds. But when we add the overheads of core reassignment, when we move the cores across collocated VMs, we can get about 3 times higher tail latency. And on top of that, for security, when we move cores across different VMs, we don't want to expose the data that was used by the first VM to other VMs running on the same core. This means that whenever we have a cross-VM context switch, ideally we want to flush and invalidate all the data that was stored in the stateful hardware structures, such as caches and TLBs. So this means that on top of 4 milliseconds, we added core reassignment and got about 12 milliseconds, and now when we add cache and TLB flushing, we go to about 16 milliseconds tail latency, which is about 4 times higher than the system with no core harvesting. So our goal is to keep the high core utilization, meaning allowing to move across VMs very fast, and increase the throughput of Harvest VM while making sure that the tail latency of primary VMs, the latency critical VMs, is still very low. In this paper, our main contributions are: 1, characterizing the opportunities to perform the core harvesting in hardware compared to software-based systems, and based on our insights to propose HardHarvest, the first architecture to do core harvesting purely in hardware. Compared to state-of-the-art software systems for core harvesting, we get 1.5 times higher core utilization, 1.8 times higher throughput for Harvest VMs, and 6 times lower tail latency for primary VMs. So first, we see that there is an opportunity when moving cores across VMs when we run microservice environments. Specifically, these services typically have small sizes, meaning small data and instruction footprints. Now, because we have moving the cores across and we flush and invalidate, if we have many misses, we suffer the performance. But we observe that microservices are tolerating smaller caches and TLBs due to this opportunity of small size and footprints. This means that we can have selective flushing and invalidating of our structures so that we can keep important data that is going to be reused in time in only small part of our caches and TLBs. We take our insights and we design HardHarvest. HardHarvest is based on 2 main techniques. First, as software overheads of core assignments are very high, we propose to do it purely in hardware. Second, as cache and TLB flushing is needed for security, but it's very expensive, we rely on the properties of small size of microservices to partition the caches and TLBs and then add some smart replacement policy to minimize the performance overheads. So let's first see how we do scheduling in these environments. Specifically, we propose to do scheduling purely in hardware. Every primary VM is assigned a few cores, and it also has a part of the hardware request queue where we store the request for incoming requests for this VM. Then, each queue has its associated hardware scheduler that we call queue manager, and we put all these structures, request queues and queue managers, in the on-package HardHarvest hardware controller. So, when a request in our system arrives from the outside through the network interface card, first we put the payload inside the LC, for example using DDIO technology, and we also inform the queue manager for this specific VM that there is a new incoming request. Then the queue manager will in-queue this request in the sub-queue for this given VM, so all the cores assigned to run a request for this VM can then dequeue the request directly from the sub-queue that stores the pointer to the payload in the LC. We use this hardware infrastructure to minimize the core assignment overheads. Specifically, whenever a queue manager sees that there is an idle core of the primary VM and there are no more requests in the request queue for this VM, it can inform the Harvest VM to use this core. So Harvest VM then uses this core, steals the core, and starts running the thread of its own. When a new request for the primary VM arrives, we store it in the request queue, and then the queue manager detects there is a stolen core and there is an outstanding request that cannot be satisfied. In that case, the queue manager interrupts the core running the stolen core running the Harvest VM request. It preempts the core and starts running our primary VM request. In this way, we move the core from the primary VM to the Harvest VM and then back to the primary VM without involving any hypervisor or software overheads. Regarding the second issue of expensive TLB and cache flush and invalidate, we propose to partition those structures. So as I said, for security, whenever we have cross-VM context switch, we need to flush and invalidate our stateful hardware structures such as caches and TLBs. Fortunately, microservices have already small instruction and data footprints that they can work well even with smaller sizes of these structures. So the idea is, whenever primary VM is running on a given core, it will use the whole structures, always in a given cache or a TLB. Then we partition this cache and TLB into 2 regions, harvest region and non-harvest region. The harvest region are those ways that can be used by the harvest VM, and non-harvest region is reserved only for the primary VM. So when the core gets stolen and the harvest VM starts running on it, It first needs to flush and invalidate the parts of the cache that belongs to the harvest region, and then it starts running populating the data in its own partition. Then, when we context switch again and return the core back to the primary VM, we can only flush and invalidate the harvest region while allowing our VM to start running even ahead of the time using the partitions that were assigned for its own purposes in the non-harvest region. Once done with the flushing and invalidating, we simply increase the size and allow the primary VM to again use the whole structure. To maximize the efficiency of the proposed partitioning approach, we also introduce a smart replacement policy. The idea is that we want to keep in the non-harvest region all the data that will be used again in the future by the primary VM across many context switches. To do that, we classify all the pages in two regions. First are shared pages. Those are typically program code, libraries, or some read-only data. These are pages that can be used by many requests of a given microservice. The second type are private pages. Those are pages that are allocated for specific invocation of a microservice. So those are private per microservice invocation. Intuitively, shared pages are more likely to be reused in the future, while private pages are going to be used only by specific invocation. So when a primary VM runs on a core and it issues an address to access the cache or TLB, we get the following data flow. First, if we have in the set all ways and then one of them is empty, we pick that slot. But if all the ways are already busy and occupied, we have two different cases. In first, if the address is shared, then we prioritize the non-harvest region with the goal to reuse that in the future. If the address is a private page, then we put it in the harvest region, so even if we lose it on a context switch, it won't matter much for the performance. We evaluate our system using cycle-accurate full system simulations with SST and Camel. We run Datacenter bench microservices, and we invoke them using the Alibaba's invocation traces. We evaluate three systems. One is the conventional no harvesting system. The second one is soft harvest, which is the state-of-the-art software-based core harvesting. And finally, we evaluate our hard harvest proposal. First, we can see that HardHarvest can significantly reduce primary VM's tail latency. Here, on y-axis, I show the tail latency of primary VMs for the three evaluated systems. Keep in mind that soft harvest is state-of-the-art software-based hard harvesting, and hard harvest is our proposal. We can see that we can get 6 times the lower tail latency compared to state-of-the-art approach. In addition, we can at the same time improve the throughput of harvest VMs. Again, compared to state-of-the-art systems for core harvesting done in software, we get about 1.8 times higher throughput. And finally, we also improve the core utilization because we allow the cores to fast move across collocated VMs. Again, compared to the software-based core harvesting, we can improve the core utilization by about 1.5 times. Overall, in this talk, we observe that microservices are an important class of workloads, but currently their utilization of resources, specifically cores, is very low. In this paper, we aim to ask the question and answer it, how to design an efficient harvesting scheme that can improve the utilization without violating the tail latency of microservices. To that end, we propose HardHarvest, the first architecture that does core harvesting purely in hardware. We are able to achieve 6 times lower tail latency for primary VMs while keeping the high core utilization and improving the throughput of harvest VMs by about 1.5 times. With that, thank you for your attention, and if you have any questions, I will be happy to take them now.